Okay, so now let's first recap the methods of transformation. So I'm just going to write down again what the formula that we did from last week. So this part, if you don't want, you don't need to take the notes again, just for a quick recap. So you already have the notes from last time. Okay, so the method of transformation is trying to handling the problem like we have two random variable x1 and x2. And x1 and x2 has a joint probability density function x1 comma x2. Okay, so the joint can be obtained from multiple ways. So one way we have seen is from the Bayesian or the conditional rules, where you can use the conditional multiply by the marginal to get the joint. The other way is that if the two variables are independent, you can just use their individual marginal, multiply them together, you will get the joint, okay? But here, let's suppose that we have the joint already, and we are interested in the following problem. Suppose a new variable, y1, has the following transformation from the x1 and x2. Also for y2, admit another transformation. So both of them are functions of the x1 and x2 together, okay? And now we want the joint distribution of the new variable y1 and y2. Okay, so the method of transformation is basically used to handle this kind of problem. And what we can do is that first we find the inverse function for the original random variable. So back then we use the function h to denote the inverse function. So the inverse function here is the input of y1 and y2, and then you will obtain the x1, your original random variable, back. Okay, so that is the name the inverse function referring to. Similarly, for x2, we can also find an inverse function whose input is y1 and y2, the new variable. After you put in input to this inverse function, you will get the original random variable back. Okay, so input y1, y2, obtain x1 and x2 back. So that's the purpose for the inverse function. Once you have that, you can get the joint of the new variable with the following formula. So you can start from the joint of the original variable. Okay, but whenever you see an x1, replace it by the inverse function. So how you can input y1 and y2 to get the x1 back. And here is that whenever you see an x1, you just replace by the inverse function that you obtain. And then similarly for the x2, replace by the inverse function that you obtain. Okay, so that's the first step. And the other step, one extra component, is that you need to multiply by the Jacobian matrix. So if you choose to use the method or the J1, that formula, then take the determinant and then take the absolute value and then multiply them together. If you choose to use the J2, also take the determinant and then the absolute value, but don't forget there is an inverse. Okay. So that's the formula that we introduced from last week. Any question or comments up to this point before we proceed to more exercise? Yeah. So this is okay. So maybe I will just use the lecture notes from last week here. Okay, so for J1 is that you take the derivative of the inverse function with respect to the new random variable. So y1, and then for the 1, 2 entry, you take the derivative with respect to y2. And then for the second row, you would take the derivative of the second inverse function, and then with respect to y1 and y2. That's your 2 by 2 matrix, and then you take the determinant of that, and then that's your J1. And then for the J2, it's just the other way around. You take the derivative from the transformation, the G1 and G2, with respect to x1 and x2, and then you get the determinant. So those are the two formulas for J1 and J2. Yes. For today's part? Yes. Yeah, this is just the same formula that we have last time. I'm just write it down again. Yeah. So this is exactly the same from your notes last week. Any other question or comments regarding the formula or the methods? Okay, if not, then now we'll just work on a few more problems as an exercise. Okay, so now let's consider the following random variables and transformation. So now let's suppose we have a random variable x that follow a gamma distribution with parameter alpha 1 and beta. And also a new random variable y that follow another gamma distribution with parameter alpha 2 and then beta. Let's also assume that the x is independent of y. Okay, so that condition itself already tells you how to obtain the joint density function for the x and y. Just multiply their marginal, you will get the joint. Okay, now let's also consider two new random variables with the following transformation. So let's say your new random variable u is equal to x plus y. And another new random variable v is equal to x over x plus y. Okay, so the question or the density of interest is the new density function with respect to the new random variable. So we want to find the joint density function for the new random variables. Okay, so find the joint density function of u and the v. Okay, so now let's apply the formula that we just seen on to this problem. Okay, so in terms of the notation from the formula, the g's for the x and y are the transformation. Okay, so if you want, you can also create a table. So the g are just the u equal to x plus y, and then v equal to x over x plus y. To use the formula, we also need their inverse. So we need to find their inverse, which is denoted by H inverse. u and v. Okay. So now let's first find a inverse function for x. Okay. So here we notice that our new random variable u is defined by x plus y, and then our new random variable v is defined by x divided by x plus y. So one way we can start from is to replace the x plus y in the denominator from your definition of the v by the definition of u. Okay, so that means v is equal to x over u, and x is equal to u multiplied by v. Okay, so again, u is defined by the sum of x plus y, and then v is defined by x over the sum. So now to get the inverse function, which is a function of u and v, obtaining the x and y in return, so we make the connection of v is equal to x divided by the sum, but now replaced by the u, because u is defined by the sum. Okay, so we have v is equal to x divided by u, and that means we have a inverse function to redefine or to get the x back. So x is equal to u multiplied by v. So that is your inverse function. So if you want to refer to the notation, the formula, this is your h1, u, and the v. So that means if you input u and v, you will get your x, your original random variable, back. Okay? So x equal to u multiplied by v is your inverse function for x. Any question up to this point? Okay, so now let's take a look, or let's think about how we can obtain an inverse function for u by making some connection here. Okay, so now we already have a replacement for x. So now let's take a look, or let's think about how we can get a function to get the y in terms of u and v. Okay, so here we know that u is equal to x plus y, and we also obtain the relationship that x is equal to u multiplied by v. Okay, so we know that u is equal to x plus y. But now we have a formula for x, so let's replace the x by the new relationship that we just obtained. So x is equal to u times v. So let's replace the x by u times v. Okay, plus y. Okay, so I'm using this one here, but replacing the u, replacing the first x in the formula from the g by the new relationship that we just obtained. Okay, so x replaced by u times v, and then we'll have that relationship. So now you can see that we have one equation that only involving u, v, and y. So we should be able to have a way to separate the y in terms of a u and the v. Okay, so this is saying y is equal to u minus u multiplied by v. Y is equal to u of 1 minus v. Okay, and this is your function of y and then h2 inverse, if you want to make the alignment to the notation in the formula. Okay, so now we have their relationship. So we know we are interested in the new random variable that are given by definition. So u is defined by x plus y, v is defined by x over x plus y. To get the joint distribution of the u and v, we need to use this method of transformation, which would require the inverse function. And in this part, we are obtaining the inverse function. So we obtain the relationship that if you input u and v by u multiplied by v, you will get the x in return. if you use the inverse function of u multiplied by 1 minus v, if you input in that function, you will get your y back. So these two, maybe let me using the color. So the thing that I underline in red are the inverse function h1 and h2. So the idea is that you input u and v, you can obtain x in return. You input u and v, you can obtain y in return. Okay. And also the right hand side should only involving u and v. And then that is your inverse function. Any question up to this point? Okay, so now we have obtained our inverse function. What will be our next step here to obtain the joint of the new random variables? To find the Jacobian matrix and determinant, right? Okay. Now we have two options, either using J1 or J2. Any thoughts on which one to use? Although they are going to give you the same answer, but we can always think about which one to use before we implement the computation part. Any thoughts? Yes.
J2.
Why is that?
X looks like it would be easier to work with.
Great. Yeah. So x is defined by some products, and then y is also defined as product. And then when you take derivative, it's easier in the product sense rather than the fractional form or the right. So J2 would be one good way to go. Thanks. Yeah. But using either J1 or J2, you'll get the same answer. But just before you choose which one to go, you can think about which one is easier. Okay. So now let's say we go with the J1, right? Okay. Okay. So now let's referring to the formula. The Jacobian matrix J1 is defined as the derivative of the inverse function. So dx by du, dx by dv, dy by du, dy by dv. Okay, once you have the 2 by 2 matrix, don't forget to calculate the determinant. Okay, so here I use the vertical line referring to the determinant. So it's based on your preference. Some math textbooks using the vertical line for a matrix to define the determinant, or you can just use a more explicit mathematical operations. And then here the dot is referring to the thing that you input. It will be the 2 by 2 matrix here. Okay, so once we have choose or decided to use the J1, now we just need to handle the derivatives. Okay, so now we know x is equal to u multiplied by v. What is the derivative of dx and du? The derivative of the u and the v with respect to u. What is our 1-1 entry here? Yeah.
With respect to u, it'll be v, and with respect to v, it'll be u.
Yes. Okay, so that's for the first row, right? Thanks. Yeah. So for the first row, for x with respect to u, we will have the v. And then for x with respect to v, we will have the u. Okay, so now we have our first row. What about for the second row? dy, yeah.
1 minus v,
Mhm.
then it'll be negative u.
1 minus, yeah, so dy with respect to du would be 1 minus v, and then dy by v will be negative u, right? Yeah. And then don't forget the determinant. Okay. Any question or comments up to this point? Yes.
Can you explain the whole H inverse thing one more time?
Sure. So the inverse function is that when you input your new random variables, you should get your original random variable back. Okay, so here we do some algebraic manipulations to obtain two functions, which is the one that are underlined in red. So you can see that on the right-hand side, we're only involving u and the v, which is the new random variables. That means if you input your new random variable, u and v on the right-hand side, you will get the x in return. And then for the second inverse function, when you input u and the v on the right-hand side, you will get the y in return. So those are your definition or your formula for the inverse function. If you're inputting the u and v, you will get your original random variable back. And this is the inverse function is also with respect to the original transformation, the g's. The g's are when you input the original random variable, you will get your u back. You will get the u, which is by definition. And then for the second g2, when you input x and y on the right-hand side, you will get the v by definition. Yes?
So just to clarify, J1 uses the inverse functions and J2 uses the original?
Actually, it doesn't matter, just a naming thing, right? But maybe I use the, so J1, so here the J1 I define as the starting from the H, right? So the numerator are all the H, okay? So now let's take a look. Our H, so on the J1 we have all the H on the numerator, right? So this is the definition for J1, yeah. It doesn't really matter too much, it's just the naming for 1 and 2. But the formula, don't forget the inverse thing, that would be the most important. Yeah. So if you start from your G's, then don't forget the inverse, which is the J2. Yeah. Question? Any other question, comments? Okay. If not, let's proceed on getting the joint. So maybe we can also find the determinant of J1, which is the product of the diagonal minus the products of the off diagonal. So we'll have negative u and the v minus the u multiplied by 1 minus v. Okay, so now let's simplify that. We'll have negative uv minus a u plus an u multiplied by v. This is equal to negative u. Okay, so that's the determinant of the 2 by 2 matrix. But don't forget, or later when you use this, don't forget the absolute value. Okay, once we have the Jacobian, let's get the joint density function for u and v. Okay, so to get the joint the density functions, u and the v, let's refer back to the formula. We need to using the joint density function for the original random variable x1 and x2. And then the only thing is just that whenever you see the original random variable, replace by your inverse function, okay? And then multiply by the Jacobian matrix. Okay, so now let's take a look or think about how we can obtain the joint density function for your original random variables. Any thoughts based on this setting, how we can get the joint density function for x and y? So we know x are,
Can you multiply them marginally?
Why is that?
Because they're independent.
Yes, thanks. Yeah, so that's what we're going to do. We notice that x and y, they all follow in gamma distribution. X and y are independent, so that means we can multiply by the two marginal to obtain the joint. Okay. So that means let's use the gamma density function of x and y and then multiply them together. Okay, so the joint for this one is equal to the product of the marginal, okay, where x and y fall in a gamma distribution. Maybe I should let me don't setting as equal sign here. So in terms of the x and y, and then we notice that we need to take the product of the two marginal, and individually they follow in gamma distribution. So now let's bring in the gamma distribution. Have the alpha 1 minus a 1 multiply by the e of negative x over beta, the gamma function of alpha 1 multiplying by beta raised to the power of alpha 1. Okay, so that's the marginal for the x. Okay, we also need to multiply by the marginal of the y. Y is defined as a gamma distribution with alpha 2 and beta. So just write down the density function in the new parameters. So we'll have alpha 2 minus a 1 e of y over beta, the gamma function of alpha 2, and then beta raised to the power of alpha 2. Okay, so here we're just copying down the density function for the gamma distribution, but with the new random variable, with the random variable x and y, and then their corresponding parameter, alpha 1, alpha 2, and then they share the same beta. Any question up to this point? Yes?
I noticed that there's a second version of the gamma function.
Yeah.
Why do we always use this version?
So basically the two versions are mathematically identical.
Oh.
It's just that you consider the rate in terms of the kind of like one is the inverse of the other one. So you consider 5 times per 60 seconds per minutes, or 1 over 20 as the rates. So that's the only difference. So 5 times, something occurring 5 times in the 1 minute is equal to 1 over 5 divided by 60, so 1 over 30 as the rates. But that's the only difference.
Okay.
It's just the other formula is just regarding beta as 1 over something, just an inverse of that. Yeah. But mathematically, they're all the same. Okay, so that's the joint density function. Again, here is due to the independence. Okay. Because they are independent, so the joint is equal to the product of the marginal. Okay. So that's the joint density function for x and y. But now we need the density function for u and v instead. And then we mentioned that starting from the joint density function of x and y, and then whenever you see an x, replaced by the inverse function h. Whenever you see a y, replaced by the inverse function h2. Okay, so now let's rewrite the joint density function in terms of the new random variable u and v. Okay, so now we encounter our first x, let's replace by the inverse function we obtain. So now we notice that, or we obtained earlier, x is equal to u and v, that's the inverse function we obtain. So here, whenever we see an x, replace by your inverse function. So you have u multiplied by v raised to the power alpha minus 1. E raised to the power of negative, so we have another x replaced by u multiplied by v over beta, divided by a gamma function of alpha 1, beta alpha 1. Okay, so what we have done here is just replacing x by the inverse function that you just obtained. You obtain x is equal to u and v, so whenever you see an x, replace by the inverse function. So everywhere where x appears, replaced by u and v. Okay, so now you can see that x is already removed from the picture. No more x showing up. Okay, for the second part, whenever you see a y replaced by the inverse function, earlier we obtained the inverse function, y is equal to u multiplied by 1 minus v. Okay, whenever you see a y replaced by that, u and the 1 minus v. So let me just rewrite that as u minus u multiplied by v. Alpha 2 minus 1 e raised to the power of, now we see another y replaced by the inverse function. So u minus u and v divided by beta. Divided by the gamma of alpha 2 beta raised to the power of alpha 2. Any question up to this point? So I've done here, just starting from the joint of the original random variable, we need the joint of the new random variable. And the idea is that whenever you see the x and y replaced by the inverse function. So now you can see the right-hand side, no more x and y involved. So this is a function involving u and the v only. Okay. Does that solve the question yet? Why is that? Or what else do we need here? The Jacobian matrix, right? Yeah. So always don't stop at this time. Don't forget there's a Jacobian matrix. Okay? Because we start from J1 and this is what we obtain. So back to the formula, we just need to multiply by the absolute value of J1. Okay? And the J1 earlier we calculate is the negative u. Okay? So we need to multiply by the absolute value of the negative u, which is equal to u. Okay. So that will be our answer. You can see that on the right-hand side, it's only involving u and v. So that is a joint density function for u and v. Now let's further simplify this object here and let's see if we can gain some insight about this joint density function. Okay, so let me group the things slightly different. Okay, so I'm going to group or separating the u and the v in a particular way. Okay, so first of all, we have a u. We have a u raised to the power of alpha 1 minus 1. We have a u here, we have a u here, we also have a u from the Jacobian. Okay, so I'm going to group the things in the following way. So here, let's start from u. I will have a alpha 1 plus a alpha 2 minus a 2 and then plus a 1. This is referring to the four place where we obtain where we have seen a u, okay? So the first alpha 1 is coming from u raised to the power of alpha 1. And then the alpha 2 is that where we have a u raised to the power of alpha 2. And then the minus 2 here is because we also have a minus 1 here and then minus 1 here. We'll have a minus 2 on the power. The plus 1 here is coming from the additional Jacobian. We have the alpha 1 plus alpha 2 minus the 2 and then plus the 1 from here. So that is the power, all the power in this function for u. Any question up to this point? Yes?
How did you get the alpha 2?
Okay, yeah. So now let me provide one more steps. Okay, so here let's rewrite the function element by elements. Okay, so here we have the u raised to the power of alpha 1 minus 1, and then multiply by v raised to the power of alpha 1 minus 1. So that is one way we can break the product raised to the same power, right? So u and v raised to the power of alpha 1 minus 2 is equal to u raised to the power and then multiplied by v raised to the power. Okay? Now let's handling this part. Okay, so this is equal to u multiplied by 1 minus a v altogether raised to the power of alpha 2 minus 1, right? Do you agree with that? Yeah. So that means we can also break this by the product, the individual component raised to their power. Okay, so u raised to the power of alpha 2 minus 1, 1 minus a v raised to the power of alpha 2 minus 1. Okay, so that will handling this part. And then don't forget there is an additional u from the Jacobian. So this is coming from the Jacobian matrix here. And now I can leave the rest as it is, okay? So maybe just for completeness, let me just write down the remaining objects. So here, uv over beta, e of the negative, u of 1 minus a v over beta, altogether in the denominator we have the gamma of alpha 1, gamma of the alpha 2, beta alpha 1, beta alpha 2. Do you agree with that, or any question for this formula? So the only thing that I did here is that I'm breaking the powers for all the u's and v. So now we have the power for individual u and v. And maybe let me also write down a raised to the power of 1 here. That's from the Jacobian. Any question up to this point? Okay, now let's go back to how we get the alpha 1, alpha 2 plus 2 minus 1. Okay. So once we break down the power for each components, here, let's complete the power for all the u's. So we have u, we have the power alpha 1 minus 1, alpha 2 minus 1, and then also a power of 1, right? So this is equal to alpha 1 plus alpha 2 minus 2 from here plus a 1. Okay, so this is where the power, the earlier, of the alpha 1 plus alpha 2 minus a 2 plus a 1 coming from. Any question up to this point? Okay, next let's complete the power for v's. Here we have v raised to the power of alpha 1 minus a 1, and also 1 minus a v, alpha 2 minus 1. So this v here coming from the second term, this one here coming from the red component here. Okay. Any question up to this point? Now let's see how we should handle the exponential term. This one and this one. Okay. So if, maybe let me just write down a few comments. So you have a raised to the power of c multiplied by b raised to the power of c. This is equal to a multiplied by b altogether raised to the power of c. That's the formula we have been using here. Or, yeah. And the other one we're going to use is that e raised to the power of a multiplied by e raised to the power of b. This is equal to e raised to the power of a plus b. Okay? That's just two formula we'll be using. Okay, so the second one is how we're going to handle the exponential terms. Okay. So here we have the exponential of negative uv over beta minus a u over beta plus a uv over beta. Any question up to this point? So I'm just breaking the power for all the exponential terms. Okay? So this one is equal to u minus u multiplied by v, but there's a minus sign here, so we end up with a plus. So this u and v over beta coming from here. The second minus u over beta is coming from u multiplied by 1 over beta. And the plus is equal to this negative sign, u and v over beta. We obtain three components here. Any question up to this point? Okay, so now I've finished handling the numerator. Let's keep the denominator as they are. So for the denominator, we have the gamma function of alpha 1, gamma function of alpha 2. So here, let me also group the power together. Beta raised to the power of alpha 1 plus alpha 2. Okay, so this is using the formula of a raised to the power of let me use b and multiply by a raised to the power of c. This is equal to a raised to the power of b plus c. Okay. Any question up to this point? Okay, let's further simplify this expression. So for u, after we simplify them, we will have alpha 1 plus alpha 2 minus a 1. Okay, and now for the exponential term, we only have the negative u over beta. Because this negative uv over beta and this plus uv over beta cancel out, so you only have one power remaining. Okay, and now we also have the u so the v raised to the power of alpha 1 minus 1 and then 1 minus v raised to the power of alpha 2 minus 1. And then a gamma function of alpha 1 gamma function alpha 2 beta raised to the power of alpha 1 plus alpha 2. So just a further simplification of that long expression. Okay, so now maybe it's going to look gradually to something that you are very familiar with. So now let's do one more manipulation here. Okay, any question up to this point? Okay, so now I want to multiply a scalar of 1. That does not alter the quantity here, right? Just multiply by 1. But now I'm going to replace this 1 by in the form of a fraction. Okay, I'm going to multiply by an extra 1 defined by gamma function of alpha 1 plus alpha 2. Gamma function of alpha 1 plus alpha 2. This is just equal to a scalar 1. Okay, does not alter the quantity, but we can multiply in this formulation. Okay. So again, the equal sign still hold, but now let's take a look. What does this extra term give us in terms of manipulating the formula here? So let me write in the following way. U is the power of alpha 1 plus alpha 2 minus a 2, minus a 1. E raised to the power of negative u over beta. Let me bring the denominator that I introduced from the scalar of 1 in the denominator here. A gamma function of alpha 1 plus alpha 2. And then beta raised to the power of alpha 1 plus alpha 2. Okay? So now I have an expression that looks like this, but just borrowing the denominator from the factor of 1 that I introduced here. Let's group the remaining terms on the second component here. Okay? For the second part, we have v raised to the power of alpha 1 minus 1. 1 minus the v multiply raised to the power of alpha 2 minus 1. And now let's divide it by the gamma function alpha 1, gamma function of alpha 2. Let's divide it by the numerator. Okay, so here, if you divide it by a fraction, the numerator will go to the denominator of this denominator will go to this will be this numerator. So I'm just replacing this numerator to the denominator of the denominator. Okay, I'm replacing this denominator just directly plugging in here. Okay, again, the equal sign still hold. But now let me ask a question. What does this formula remind you of? What does that formula represent? Yeah. What specific of gamma? I need a name. PDF, right? The thing that we introduced in before midterm 1. So this is the probability density function of a gamma distribution. Let me ask a follow-up question. What is the new parameter here? What is the alpha for this gamma? And what is the beta for this gamma? It's the new alpha, right? Yeah. Where's the beta? Just the beta itself, right? Exactly. Thanks. So the equal sign that still holds throughout the manipulation ends up with this particular term. We're recognizing this is the density function for the gamma distribution. And then the new parameters are the new alphas are the alpha 1 plus alpha 2. The new beta are just the beta. Okay. So now let's write down one intermediate result. This is the gamma function of alpha 1 plus alpha 2 with the parameter and also beta. Now the question is, what does the second term represent? mathematically or statistically. So there's a name for this one. This is called a beta distribution with parameter alpha 1 and alpha 2. Okay, so in practice, people usually don't like this whole fraction term here. They just define a beta function, alpha 1, alpha 2, by the things that we have here. Plus alpha 2. So this is called a beta function. So now if you replace this b, capital B of alpha 1, alpha 2 with this numerator, then you have obtained a probability density function of a beta distribution. So that is also a new distribution. And one more comment here. Here we can write as the product of the two density function. So now my question is, what is the relationship of the u and the v for the new random variables?
They're independent.
They're independent, right? We can write the joint in terms of the product of the two marginal. That means u is independent of v, such that u following a gamma, alpha 1 plus alpha 2, beta, v following a beta distribution of alpha 1 and the alpha 2. Okay, so this is something you can conclude. Just go back from the top. We have two gamma random variable, x and y. Okay, our new random variable is u, defined as the sum of two gamma random variable. V is defined as a ratio. Okay, so earlier, probably somewhere in week 5 or 6, we showed that the sum of the gamma is also a gamma, right? So this is a gamma divided by gamma, defined by v. Okay. Throughout the method of transformation, using all the formulas, you obtain this density function. And we notice that this is this part from the manipulation, density of gamma. This part, density of beta distribution. It can also be represented by the product of the two marginal, giving us their relationship of independence. Okay? And that is all the information that we can obtain from the method of transformation from two gamma distribution. Okay? We obtain a gamma and a beta distribution. Any question up to this point regarding Yes.
Sorry, this is going back a little bit, but going back to like how you calculated the joint, like like more
keep
back,
scrolling up.
like J1.
Yes.
Like, yeah, it's
J1 here.
Yeah, I'm kind of confused how you go from like the first word to the second one.
The first determinant to the second determinant.
Yes.
I see. Yeah. So it's just here. So this is your two inverse function, right? Do you any question up to this one? Oh, good.
Yeah.
So I'm just applying the formula for dx du. So that means I'm going to take derivative of this with respect to u, right?
Okay.
So derivative of that with respect to u is v.
Oh, got it. Okay. No.
Derivative of x with respect to v is u.
Got it. Alright.
And then for that one with respect to u is 1 minus v, the second term. For this one is the with respect to v is the negative u, right? We have that. And then AC minus BD, the product of the, yeah, that's the determinant. And the Jacobian here, the determinant, we have a negative sign, so don't forget about that. But that negative sign will be handled by the absolute value here. So this vertical bar is the absolute value, and that vertical bar is the determinant of a matrix. Yeah. And then one more thing is just that the u here contribute a factor of power of 1 in the minus a 2 plus a 1 minus a 1. become the factor for the alpha that you just identified, right? Yeah. So the minus the 2 minus the minus the 2 plus the Jacobian ends up with minus 1. That's the minus 1 from the gamma distribution. Okay, so we have seen actually 3 exercises for the method of transformation, each of them giving you lots of insight, actually. So here you have seen a new distribution. I'm not going to test you on that, but just more of an FYI. You can always get very new distribution from different manipulations. Yes?
When you got the beta distribution from like the V term, what happened to like the V to the alpha 1 minus 1 times 1 minus V? Like, is that part of the beta distribution, or is that just like...
Oh, okay. So let me write down so the probability density function of x, where x following a beta distribution with parameter alpha 1 and alpha 2 is f of x equal to x raised to the power of alpha 1 minus a 1 minus a x of alpha 2 minus a 1 over the beta function of alpha 1 and alpha 2, where beta function is defined as the product of the gamma function over a gamma function. And that is the density function for that. Does that answer your...
Yeah, thank you.
Any question up to this point? Okay, so it seems like we still have 30 minutes. Then I want to introduce. So my goal is still going to provide you another exercise that gives you insight of a new distribution of statistical properties. So you can see that from the method of transformation, you can obtain more insight. So my next goal is to, using the method of transformation, to introduce you the T distribution, okay? And then T distribution, I'm pretty sure you all use it, it's just you didn't recognize or realizing you are using the T distribution for your like a T-test, where you have a treatment group, control group, you want to test their your effectiveness of a drug or something like that. You are all using the T-test, okay? And now I'm going to introduce, through the method of transformation, introducing the T distribution. Okay, but first of all, there's one more distribution I want to introduce. And also, I'm not going to test you on these new distribution. It's just a quantities or things that can lead you to the insight. But the idea or the thing I'm only going to test is whether you can use the formula for the Jacobian for the transformation to obtain something that I ask. Okay, but I'm going to do the exercise, but using the exercise to introduce you more statistical concepts as an FYI. Okay. So now, that's the first thing I want to introduce you is the chi-square distribution. And then I'm going to use that to introduce to the T distribution. Okay? And by seeing all these things, you need the method of transformation. Okay? So it's a very powerful tool to introduce you or to obtain lots of statistical insight. Okay? And the first thing I want to introduce is the chi-square distribution. Okay? And also, the chi-square distribution can be obtained from the standard normal distribution. So again, lots of things are all connected through the probability density function that we introduced earlier in week 1. Okay? So now I'm claiming that if I have Z1, Z2, all the way to Z, let's say, let me use a letter K, okay? ZK. Each of them independent, identically distributed with a standard normal distribution. That means mean is 0, variance equal to 1. Okay, now I'm claiming that if I take the summation from 1 to k, zi's, taking the square, this new quantity here, let me introduce a new distribution, it's called chi-square distribution. Okay, and chi in, I think in English is writing chi squared. And then the k here is referring to the degree of freedom equal to k. Okay. So earlier you have seen the relationship between Poisson and binomial distribution. That is for the discrete random variables. Now I'm going to show you some connection for these continuous probability density functions, specifically focusing on the standard normal, chi-square, and t distribution. So these are all new distributions in the continuous random variables. And now I'm going to show you their connections for these continuous regime. Okay, so each of them follows standard normal, taking the square, taking the sum, you obtain a chi-square distribution, degree of freedom k. Here, I want to analyze the moment generating function of this thing here. So let's also give a name, v, to this summation here. Okay, so now my question is, what is the moment generating function for this new thing that I just defined? Okay. So now circling back to our like before midterm 1, what is the definition or what is the properties for moment generating function? Oh, one more thing is that don't forget they are independent. Okay. So I'm asking for the moment generating function of a sum of the independence random variables. What are some properties we can use? So the moment generating function, if you still recall from the property 1, the moment generating function of a sum of an independent random variable is equal to the product of the marginal moment generating function, right? So this is equal to the marginal of z1 square multiplied by the marginal of z2 square all the way to the zk square. Okay, this is property 1 when we introduce the property of the moment generating function. Moment generating function of the sum is equal to the product of the individual. Is there any question over there? Okay, so now we need to handle the moment generating function for the individual standard normal. Okay. Because they are independent or identically distributed, and we replace by the products, so we can just handle with using one random variable zi. Okay. Now, using the definition of the moment generating function, this is the integral of the e raised to the power of tx. Okay, here our x is the zi squared, and then multiply by the density function. So here I'm only using the definition of the moment generating function. So you can refer your lecture notes from week 2. The definition of the moment generating function is that e of tx multiplied by f of x, and f of x is coming from the standard normal. I think you can refer to your lecture notes from week 5 to obtain the density function 1 over 2 pi e raised to the power of negative 1 over 2 zi. So this is all just coming from the property of the homogeneous function and the definition of the homogeneous function. These are, you can obtain these from your lecture notes from week 5. Okay, so now we just need to manipulate in the following way. Any question up to this point? So the first few lines is just using properties and definitions. Any question up to this point? Okay, next I'm going to manipulate in the following way. The product of 1 to k. Again, I'm going to multiply by a factor of 1. But I'm going to multiply that 1 by construction in this way. 1 minus 2t raised to the power of 1 over 2 over 1 minus 2t negative 1 over 2. Okay? This is just a factor of 1. And an equal sign still holds. Okay? Okay, so here, let me group so first of all, in the beginning, I multiply by a factor of 1. The constant 1 over square root of 2 pi here. So for this part, I'm going to group the e raised to the power of t zi squared with this one. I think I'm missing a square here as well. So the density function, don't forget there's a square. Okay, so my next step here on the last component, I'm going to group the two exponential terms together. Okay, so again, e raised to the power of a multiplied by e raised to the power of b is equal to e raised to the power of a plus b. Okay, and now let's rewrite the a plus b in the following way. So this is equal to e of ti zi squared let's see, minus 1/2 zi squared dz. Okay, so this part is slightly tricky, but let me just give you the result. Okay. Through some manipulation of this term here, let me underline in red for this part. This is equal to e, let me write it, the exponent. So this part, it's a little bit tricky, but I'm just going to provide you the result for now. This is equal to negative zi squared over 2 times 1 minus 2t negative 1. Okay? If you're interested, I can talk about this particular detail, but this is just some algebraic tricks that you can rewrite something multiplying by 2 over 2 and then make it in the denominator, raised to the power of -1. So some tricks, but let's now assume, just I'm saying that these are the same, but it's slightly tricky. But now let's just obtain. Let's assume that we have this result for now. Okay. If you're interested, I can show you later how you get those steps. Okay. So my question here. Maybe let me provide one more extra step, and then I will ask a question. One minus a 2t 1/2. Because that is a constant, so the numerator is a constant with respect to z. So we're taking a derivative integral with respect to dzi. This thing is a constant with respect to z, and bring it outside to the integral. You will have 1 over 2 pi 1 minus 2t negative 1 square root of that e the exponential term negative zi 2 1 minus 2t negative 1 dz. Okay, so these are the manipulation that I obtained, that I performed. So the high level idea again from these 3 lines is that I first multiply by a factor of 1 in this form, and then I group these things in this form. I didn't show you the details, but now let's assume that this is correct. You have that, and this one is a constant with respect to z. I bring it outside to the integral. Now my question is, what does the formula inside the integral reminds you of? Does that look like something that you're familiar with? Yes, exactly. Now the follow-up question is, what is this new normal distribution, the mu and the variance here? So we're recognizing the things inside the integral is a normal. Okay, that's correct. My follow-up question is, what is the mean here? What is the variance here? So if you look at the formula for the general normal distribution, you have the zi minus u over 2 sigma squared. So here, the mu here is kind of like a minus a 0. So you can write it as zi minus a 0 altogether squared. So this is telling you the mu, the mean, is equal to 0. What is the variance here? One minus 2t inverse. Okay, so that is the thing we obtain inside the integral. So we know this, the thing inside the integral is a density function of this normal distribution. And the integral of the density function, what does that equal to? Just 1, right? So everything disappears. Equal to the product 1 minus 2t raised to the power of negative 1/2. Okay? Everything is a constant. So the product with respect to the subscript index I here, it's just k copies of them, right? You will have 1 minus 2t raised to the power of k over 2. What does this formula remind you of? So don't forget, we are calculating the moment-generating function of v, where v is the sum of the square of the zi's. What does this formula remind you of? The gamma distribution. Right? What is the alpha and beta here? So this is saying, using the uniqueness theorem, right? We have identified that gamma, this v following a gamma distribution. What is the alpha again? k over 2, right? What is the beta here? 2. Okay, so this thing that I earlier say is defined in this way, this is called a chi-square distribution. But through manipulations of the moment function, you can see that chi-square distribution is essentially a special case of the gamma distribution. Okay, so this is called chi-square distribution, degree of freedom k. But essentially, it's just a gamma random variable. So now I have seen lots of connections for all the probability density function in the continuous regime. So we have seen that the sum of exponential distribution is a gamma, and exponential itself is a special case of a gamma. Here we introduce a new distribution chi-square, but we can see that it's also a special case of gamma. And then we also, through the gamma distribution, we can see that using the method of transformations, you also see there's a beta distribution showing up. So you can see that by manipulating the probability density functions, you can obtain some other new density functions. And then if you're interested in the probability, if you use these density functions to measure your quantity, your events, let's say the 2 routes problem in the midterm or in your business setting or in your control treatment experiments, you can all use these density functions to calculate the probability. So what is the probability that your treatment effects is statistically significant than your control group? So you can all use these density functions to calculate the probability to answer all these questions. But again, all the foundation lies on the probability density function, the moment generating function, and their manipulations. Okay, so maybe I'll pause here, and then next lecture, I'm going to use the method of transformation to introduce you the t distribution through the normal, through the chi-square distribution.